Hi everyone, my name is Neha Dikshit and today I'll be going through a time series analysis of smart home temperature forecasting data. First, let's understand the motivation behind this and the goals set to achieve. While efforts are being made around the world to minimize the greenhouse gas emission and make progress towards a more sustainable society, global energy demand continues to rise. Building energy consumption accounts for 20 to 40% of the total global energy consumption, and heating, ventilation, air conditioning answer to around 50% of this amount. Therefore, implementing energy efficiency related strategies and optimization techniques in a building is a critical step in reducing the global energy consumption. Adding a little bit more context, the University of Spain built a solar house to participate in the Solar Decathlon Europe 2012. Such constructions become a research facility that the university employs in order to test innovative solutions around the area of energy efficiency. A lot of technologies have been integrated to help to reduce the overall power consumption of the house. The predictive system based on artificial neural networks was developed as one of them. A system like this generates a short-term forecast of the indoor temperature, utilizing data acquired by a complicated monitoring system as input. The system expects to reduce the power consumption related to heating, ventilation, and air conditioning systems due to the assumption the high power consumption of which HVAC is responsible, and the energy needed to maintain temperature is less than the energy required to lower or increase it. The goal is therefore to reduce energy consumption by predicting the indoor temperature of a room in order to choose whether or not to activate the HVAC systems. These predictions could allow the house to adapt itself to future temperature conditions by using home automation in an energy efficient manner. So in this case, exploring the data, let us know that the data set is collected from the monitoring system mounted in a solar house. The data set corresponds to approximately 40 days of monitoring data. The goal is to predict indoor temperature of a room in order to choose whether or not to activate the HVAC systems. The data was sampled every minute, computing and uploading it smoothed with 15 minutes mean. It has been established that the power consumption attributed to HVAC accounts for 54% of the total consumption, and the energy around to maintain the temperature is less than required to drop or raise it. As a result, a predictive model capable of predicting a room's indoor temperature would help in lowering overall energy consumption by deciding whether or not to activate the HVAC system at appropriate time. So I'll start my analysis with the univariate analysis, where we are looking at our target variable, which in this case is indoor room temperature data. Here is the original data, the sample autocorrelation and the spectral densities that, as you can see, the autocorrelation are slowly damping as the lag increases, indicating that for the lags up to and at least 25 pair of observations lag unit apart tend to be on the same side of the overall mean. Practically, this means that the series will tend to be wandering, and it does show that the data is non-stationary as it violates the condition of non-constant variance. So after the further doing in the univariate analysis, looking at the data, I went ahead with the applying the first difference transform. I look at the data set and found a seasonality factor by observing and looking at the frequency peak of 0.0104, which corresponds to a period of 96, which is actually in line with the data computed, which is every 15 minutes, which is in every 15 minutes interval. So after handling the seasonality, both AICs and BICs recommend an ARIMA 3.2 model, which gives an ASC of approximately 4.45 over a 10-day period. As you can see, here are the forecasts along with the confidence interval for ARIMA 3.2 model. Now moving over to the multivariate analysis, which is basically in order to forecast more accurate results by considering the impact of other variables which are significantly impacting the indoor temperature variable. I went ahead plotting those variables to better understand them. Applying the VAR model, which seems to be poorly performing compared to ARIMA model, ARIMA 3.2 model, the ASC came out to be 5.19. Running the model through MLP, which has inputs of various lags of all variables and 5 hidden nodes to result in one output, the ASC came out to be 1.5497. So comparing the various models, looks like the MLP was by far the better performing model. I did run the data through ensemble model where I combined the two better performing models, which in this case are MLP and ARMA. However, the ASC was still a little less compared to the MLP. So hope this information is helpful and informative. Thank you so much.